I will do something which I wasn't going to do, but in the end I decided to. So what I will be doing today is an explanation of the notions we didn't develop that much, but we will in the next lecture, namely regularity and smoothness. So I will explain how the geometry of algebraic variety is related to the commutative algebra of its ring of regular functions. In particular, why some algebraic varieties can be interpreted as smooth manifolds with singularities. Of course, then I would have to define smooth manifolds, and I would spend some time on that, but not that much. So I will sort of remind you what is the definition, because it's impossible to give that a full attention. Okay, so first, what is a manifold? A manifold is topological space. So it's continuous manifold, not smooth manifolds. Locally homeomorphic to Rn, or an open ball, which is the same. And of course, you have group of homomorphism acting on a connected manifold, and this should be the same as notion of a manifold, but in fact it's an open problem that there should be some set of conditions which make sure that a topological space is a manifold when it is homogeneous, but it's not known. Anyway, so the idea is that manifolds are sort of homogeneous topological spaces. Topological spaces huge automorphism groups.
So exercise is an open problem?
It's an open problem. Exercise, no. It's the opposite. So if you have a manifold, it's connected, then it's a group of automorphism extransitively. It's not hard.
Yeah,
but converse is hard. You can try to characterize manifolds as topological spaces which with homogeneous automorphism group and some extra conditions. It's a question of geometric topology, which is still not, I don't think there is a clear answer to that. Of course, you need connectedness, you need local connectedness, you need local simple connectedness, and something else, but local compactness, still it's unclear. Yeah, it's not locally connected. No, you definitely need local path connectedness, you need local compactness, but it's not enough. And local fine dimensionality by Lebesgue, it's still not enough. Okay, and before I go on, I'm telling you the Banach fixed point theorem. So if you have a map, it's a statement, here I wrote it for subsets in Rn, but in fact it's true for all complete metric spaces. If you have a map from M to M, f of distance from f of x to f of y is less than c times distance from x to y, and M is complete, this implies that there exist fixed points. There exists C, how I denote it? Well, fixed point. So if it is true, for instance, for a closed ball, we need it only for closed balls. So here on the slides I stated for closed subsets, doesn't really matter. So the idea is you take f you take x, f of x, f of x, and so on, and you check that it is Cauchy sequence, and it converges to sending because our manifold is complete. Metric space is complete. Here I did it for sequence of points in Rn, which is also true. And this fixed, the limit of this sequence is fixed point because if you apply f to this sequence, you obtain itself.
But you apply it to a closed subset of Rn.
Yeah.
It needs to be closed and bounded.
Doesn't matter. As long as it's complete, it works because it's true for all complete metric spaces. So it's all closed subsets of Rn will work because they are complete. Anyway, here I wrote it for the most elementary terms, just that the people who don't know any topology and metric spaces can follow. We still don't have time, so I won't give it on the blackboard, but it's elementary. And of course, you can find a counterexample. This is an exercise, for instance, an open ball which is not closed. Then you can find a very easy counterexample. So closeness is necessary, compactness is not. You don't need that to be compact. In fact, it's true for Banach spaces where Banach actually proved it first. Okay. Now, what is a differentiable map? And again, it's something that everybody knows. So you have Rn to Rn affine maps. R is linear plus constant is affine. And then f is differentiable. Is differentiable if f can be approximated by affine at every point where it is defined. If it's defined on Rn, it's Rn. It's defined on some u in Rn, it's on u. And approximation is given as written there. So you take f minus a. We are interested in this we take x0, we take f of x minus a of x. This is divided by x minus x0. And the limit as x goes to x0 should be 0. So it should converge to, well, this means that they are tangent in this graph of a of x is tangent to graph of f in the point x0. This is standard. I hope I don't say anything new. What is diffeomorphism is a map which is differentiable, and the inverse is also differentiable. F diffeo if f differentiable and f minus 1 also differentiable. And in fact, differential of diffeomorphism is also an invertible map which follows from chain rule, just composition of derivatives, the law of composition for derivatives. If you have two functions, they are approximated by affine, then their composition is approximated by composition of these affine functions. And then if you have f g is identity, then derivative of f times derivative of g is identity. Okay. Now, why did I give this definition? Because I wanted to state inverse function theorem, which is will be used to study smooth manifolds, and in fact to define them. So theorem. Suppose you have f from x from u to v, where u and v are subsets in Rn, and f differential of f in x is invertible, and f is differentiable. Differential of f is invertible, then f is diffeomorphism in a neighborhood of x. X is a point where it is differentiable, when it is invertible. So the proof is as follows. Well, first we replace f by, well, let's call this differential of f a by f multiplied by taking composition with minus a, minus 1. Then differential in x of f is equal to minus identity. Okay, and I will also assume that f of 0 is 0 and x is 0. I will just move the center to 0, like move coordinates to x, the center of coordinates to x to simplify notation. Okay, now we're interested in a solution of equations. F of x is equal to c. This is the same as f of x plus x is equal to, let's write it like that, minus c is equal to 0. And this is equivalent to f of x plus minus c is equal to x. So consider now function g, which is equal to g of x is equal to f of x plus x minus c. Then we are interested a fixed point of g is the same as a solution of f of x is equal to c. Right? So this is g of x. So solution of this is the same as solution of that, and this fixed point of g. On the other hand, g of x, the derivative of g of x is equal to 0. And this implies that g of x divided by x, limit as x goes to 0 is 0. In particular, for a sufficiently small ball, this implies that G actually has this property. So there exists a sufficiently small ball such that this g of x absolute value is less than 2, well, x by 2. And in fact, moreover, you can also assume that g of x minus g of y, again, because it's approximated by 0, it will be less than x minus y. Because it's approximated by 0 map, its derivative is 0. So it's a contraction in this sense. And applying Banach fixed point theorem, this gives a unique fixed point for x. Of course, you need to choose an open ball where it is true, and this is what we need to do. And inside this ball, we find a smaller ball, which is closed, and for which this will be also true. And for this closed ball will contain a fixed point of g. Clear? Good. I suppose that everybody should know this by now, but just to simplify matters, okay. This was needed to define the manifolds. I hope I won't spend much time on this. Sorry, please accept my excuses if you already know this very well. Now we are interested in maps, smooth maps, f from Rn to Rm. It's a smooth map, so it's a regular point is x in Rn such that df, the differential in the point x, is surjective. And regular value is a point y in Rm, in Rm, such that all x in pre-image are regular. It turns out that this is a generic condition. General point, this is called Sartre lemma. I'm not going to use it. But this is a nice condition. It's generic, so it holds for almost all, well, outside of measure zero set. So it really holds for almost all points in Rm. Okay, now I can define smooth manifold, submanifold. Definition. It's not abstract manifold, which is defined in terms of charts and atlases. It's submanifold in Rm. So n, or is it m here? Yeah, it's m in Rm. It's called smooth submanifold. If every point x in M has a neighborhood, diffeomorphic, well, equipped with diffeomorphism, neighborhood U, phi from U to an open ball diffeomorphism, and M is phi minus 1 of a linear subspace. This thing is clearly a submanifold, a manifold, because in topological sense, because it's locally diffeomorphism. But now this diffeomorphism is provided by a smooth map. This is why it is called smooth submanifold. And the theorem, which immediately follows from, well, I will next slide it will be seen the way it follows, but it does, is the following. Suppose you have a regular value of a map, so theorem. You have f from Rn to Rm, smooth, and y inside Rm is regular value. Then f minus 1 of y. So generally we assume that n is bigger or equal than 2m. Typically bigger because we are not interested in zero-dimensional manifolds. But if it is smaller than m, then it would be just empty, because then there is no point where it can be surjective. So regular value is the value which has no preimage. So it makes sense for n smaller than m, but it's empty. Then f minus 1 of y is a submanifold. Good. Okay, so let's prove it. The proof immediately follows from this inverse function theorem about the. So what we need is we need to add a certain number of variables to modify the map f so that it becomes a diffeomorphism, and then it would the inverse would give us this map to be. So proof. I would f from Rn plus L, to Rm plus L, where L is a vector space of dimension Rm n minus m. And this would be a direct sum of f plus a map called, here it was called A. So what is L? L is kernel of df. And A is any map, any linear map, which induces isomorphism from kernel of df to L. Okay, then this map is clearly surjective. So it is an isomorphism because the dimension of Rm and dimension of Rm plus L is the same. So d of f plus A is isomorphism. Then this map, the new map, let's call it Fa. The new map Fa is an isomorphism. So what, and it maps, so Fa minus 1 from 0 plus L is the same as f minus 1 of 0. Well, here I again assume that we take our y is 0. So we assume that y is 0, and we prove the f of 0 is 0, and we prove this statement in the neighborhood of 0, just to simplify notation. I increased the map by a linear map, and the preimage of this preimage of the space L under this map is precisely preimage of 0 under F. So this is, and this map this new map FA is diffeomorphism by the inverse function theory. I hope I was clear. Was I? Good. Okay. It has the only corollary which we need. In fact, we need it only for one, but it's still nice. So suppose you have an subset, M a set of solutions of equations f1 of x is equal to f2 of x, and so on. F equal to fd of x is equal to 0. And suppose that at point y in Rn, so these all equations on Rn, at y of Rn, we have differentials. These are functions. So fi is functions from Rn to R, or Cn to C. In fact, you can do the same with complex. Suppose that you have the space generated by the differentials, which are one forms on Rn, so they are covectors. The fd is d-dimensional. Then this set of equations defines smooth submanifolds. Then f(x) equal f1 of x is equal to f2 of x is equal to some f d of x equals 0 defines a smooth submanifold. This is interesting even if you have just one equation, because this means that you have a subset defined by one equation, and this condition that it is d-dimensional means that it is non-degenerate. So this is a smooth submanifold. This is just because it's preimage of a regular value. Of course, the point okay. And then I have an abstract definition, which I'm not going to repeat that much because everybody probably heard about it. And if you didn't, then you don't care because I'm not going to use it. So the idea is that, but it's nice definition because it's the same object, but it's chart and it's independent on the embedding to an ambient manifold. So you have a set of charts, open subsets, which are all diffeomorphic to Rn. And you have the gluing function. This gives you coordinates. Locally, you have coordinates. And then you have gluing functions, which are change of coordinates. They should be all diffeomorphic. Then you can ask for them to be certain classes, like differentiable, analytic, smooth, which is infinite differentiable, and so on. I guess I can just skip it, right? This is one notion which we need. Another is covering maps. So let's define it. So definition, f from m tilde to m. Well, this it's at C-W complexes, forget it. It doesn't matter. It's some kind of topological spaces for which this notion makes sense. So we have a smooth map. Oh, sorry, just continuous map. And it is a covering. Is a covering if for each point x in M there exists a neighborhood U such that the preimage of U is several copies of U. So it's identified with several disconnected copies of UI as a topological space, and then for each of these copies, the restriction of phi to this UI from UI to U is a homomorphism. This is a very good notion if you are interested, for instance, in fundamental group, because you can use it to compute fundamental groups. And for many other purposes, we won't use it much, these consequences, so I skip most of the context. It's really important to learn if you suddenly didn't know. Okay, but I would give one at least important example definition. You have group gamma, a group. Typically, it's finite group. We're not interested in that moment in topological groups, Lie groups, just discrete group with discrete topology. So discrete means that just we are not putting any topology on it, essentially. So acting on M, which is locally compact. And suppose that quotient, the quotient makes sense. What is a quotient? It's just the quotient set with topology, where open set is just a set where preimage is open. So suppose that it is Hausdorff. Then the action of gamma is called properly discontinuous. Typically, you define that notion. You can look in Wikipedia in more complicated terms, and then you prove that it is Hausdorff. But in fact, this is for locally compact, this is equivalent. You can define that in bigger generality, and then it would be hard. So it's, and we don't need anything except Hausdorffness for all applications. Now there is a theorem which is really almost, I leave it as an exercise, but it's a good and it's not very complicated exercise, except that, yeah, let gamma be a group. So it, I said it on M, but M should be locally compact. Well, it is a manifold, so acting on a manifold on a manifold. So the best generality for all this is that you have a space which is locally compact, locally connected, and locally simple connected. But manifold is enough. Freely means that there are no fixed points, and in fact, all orbits have the same. I mean, gamma acts transitively and freely on orbit. I mean, gamma is has the same number of elements as in any orbit as an orbit. So there is no point which is fixed by a non-trivial element of gamma. Action on them freely and properly discontinuously. Then M goes to M by gamma is a covering. In fact, this is almost if and only if. If you remove freely and you ask for stabilizer of each point to be the same subgroup in gamma, this would give you all coverings. So this, there is a certain bijective correspondence between coverings and subgroups in a fundamental group, and then you can obtain every covering map by taking a group quotient. For us, it's very convenient, well, if we would do algebraic geometry and not commutative algebra, because in the finite quotients by the group actions, they make sense in algebraic geometry, as I proved. In fact, I proved that at some point in this course that the set of invariants by the group action is algebraic variety, if you have algebraic action of a finite group. Okay. So let's do something for a bit more, just some examples in geometry. First, you have example. You have S1 goes to X1. S1, it's a Zn quotient. So you have S1 is R quotient by Z. And then you have a multiplication by D from to R quotient by Z. And the preimage of every point is torsion points. So it's like F minus 1 of Z is Z divided by D, right? So it's the same cyclic group, but D times, taking D times, so it's like every point has D preimages. This is why it is a covering. So it's D, you can make a picture. So it's D-sheeted covering. I will do it for 2-sheeted, for 2 it's probably easiest. So you have this 2 times this helix of 2 sheets covering S1. Of course, you can do the same with 3. It's slightly more difficult to draw, but it's possible. And this goes to again to a circle. Well, I can do it for ND. This is the first observation. Yeah, the second is that the number of preimages is constant. Well, I'm not going to use it, so I'm not going to give you the proof, but it's obvious because it's locally constant. So locally, preimage of a point of U is several copies of Ui. So preimage of points which are on U has the same number of every point in U has the same number of preimages. So the number of preimages is locally constant. So if you have a covering of a connected manifold, its number of preimages is the same for finite covering. And it makes sense to give a definition. This is if you have so definition. So F from M1 to M has degree D, so covering if the number of preimages of X is equal to D, and this is also called D-sheeted covering. Yeah, and of course, with compact, if M is compact, then every covering has finite number of finite degree. Every point has finitely many preimages. This is because if you have this disconnected union, then any point in for any point in U, its preimage is a set of infinitely many points with disconnected neighborhoods. So it has no limit point, and in compact, every sequence has to have a limit point. So you cannot have infinitely many, infinite degree for compact sets. Should I go on? Good. Okay, now I'm reminding you so why did I do that, all these things? This was, I was going to explain something I mentioned a lot, namely that the Noether normalization lemma is in fact a very nice geometric statement about the complex varieties. This I'm going to prove today. So let me remind you what we had already. So we had the following two statements, which is like, well, we had three versions of Noether normalization lemma and this nice proposition. So this is what the statements I'm going to interpret geometrically today. So proposition. Suppose you have a X in Cn. And then you have z1 dot zk. These are coordinate functions. Which give transcendent basis. Transcendence. Then after a linear change of coordinates, which is written down here, as Zn, considered as a function on X, is a root of monic polynomial. With coefficients in coefficients in the polynomial ring of z1 dot zk. This was the algebraic statement, and it has a geometric interpretation, a corollary one, which is our Noether normalization lemma, the first version. So you have X inside Cn, and you have the same assumption, z1 dot zk transcendence basis. Then you need to change your coordinates a bit. Then after a linear change of coordinates, we change the coordinates in such a way that this becomes true for all coordinates after the first k. So we change coordinates according to this rule for all n. The projection the projection map x to ck to the first k coordinates is finite. In particular, every point has finite number of preimages, and if you count them with the multiplicities, it will be the same. I'm not sure I proved that, but it's still true. Okay, so the idea, what I'm going to do today is to, I will prove that this map is a covering. Outside of certain divisor, this will be covering, and what is called, then this divisor will be ramified. There could be some multiple preimages. The same point can have like, the preimages can have multiplicity, so the sheets of our cover will come together at these special points which are divisor, but outside of this divisor, this will be a covering. And this is the geometric meaning of this Noether normalization lemma. So I'm going to prove this today. So I was mentioned that multivariate functions a lot. This was actually the root of the reason why Riemann defined manifolds. So in fact, it's sort of, this notion predates manifolds, but I will define them in terms of manifolds, of course. First, I'm going to define complex manifold. Well, it's the same as usual manifold, but instead of having translation functions smooth, you have translation functions which are complex differentiable. So it's M with chart UI, which are isomorphic to open ball in Cn, and transition functions, complex differentiable. So this was, of course, when Riemann first defined manifolds, he was actually interested in complex manifolds of dimension 1. And people realized that this is a very good notion. Well, it was probably Poincaré who realized that much later. And even Poincaré was mostly interested in Riemann manifolds, but Riemann surfaces, but he sort of realized that it makes sense for any dimension. Okay, so complex subvariety. If you have M inside, well, X inside M, so M is a complex manifold, which will be typically Rn, but it doesn't really matter, is a complex subvariety if X is given by a set of complex analytic equations. So why I'm doing that instead of doing usual algebraic geometry when we find the same notion but in terms of regular functions? This is because I'm going to do this maps, these covering maps. And the point is that these maps are n to 1. They are locally, they are like diffeomorphism, but the map, the inverse map is never regular. It's some root of, like it's algebraic function which is not regular, something like square root of z, for instance. There are shortcuts allowing you to do it algebraically, but it's still much harder than and completely geometrically impossible to grasp if you don't know the analytic side of the picture. So still it makes sense to define it analytically and then go to algebraic geometry. So this is why I'm doing this in complex analytic language and not an algebraic language. Okay. Now what is a multivalued function? Suppose you have M, a complex manifold. You have Z inside M times C. Z is a multivalued function. From M to C. So the idea is that it is defined, but it might take several values at each point of M. So we take a projection from Z if the projection from Z to M is locally a diffeomorphism outside of a closed subset, nowhere dense subset of M. So for each point outside of this set, this multivalued function takes this point and gives, so it's a f, I put quotes because it's not really a function. It takes M and puts it to a pi minus 1 of M inside Z. So you have pi, and we take its preimage. So it's a subset in C. Well, it's subset in C times M, but we're interested only at C. So the values are taken in C, but it can have several values. So typical example is logarithm, which is not well defined on, I mean, everybody works with logarithm, but in fact it's not well defined. And this was something that people who do like first year complex analysis know very well, because you need to always work, well, not only with logarithm, the same with square root or third degree root or something, but typically people do it with logarithm. So example. Logarithm is a multivalued function. From C to C. Because you have its graph. Z is the set of all y, xy, such that y is exponent of x. And this is a subset in C2. And you have a projection. So you have a projection from Z to y. Up. You want to invert. Yeah, you want to find all x which have this property. If you know y, then x is logarithm.
We know that this is a locally diffeomorphism by inverse function theorem.
Yeah, because exponent has, thank you. It's in local diffeomorphism by inverse function theory because the exponent has diffeomorphism which is just invertible. So now Z is one-dimensional. It's a complex submanifold, also by inverse function theorem, by the way, because this equation, this is something we had, that the equation with non-zero derivative defines a submanifold. This is the submanifold. And it's not only subvariety, but it's even a submanifold. But the important thing is that it is defined by this equation. And in fact, for each non-zero point, you have this it's a Z covering, and I mean covering which group Z acting. And For 0, there is no preimages. So this Riemann surface, the Z, I mean this complex variety, is in fact it's like infinite covering of C without a point. So you have this. It's hard to draw, but you have this kind of infinite helix projection to C without 0, and this is C. And this is exponent. And logarithm is inverse. But it's multivalued, of course. Okay, so another example is a root. So you have y goes to y some root of a degree. The corresponding Riemann surface Z is the set of all xy such that y is x power n. It's n-to-1 covering outside of 0, and 0 has 0 only preimage 0, so it's ramified. When it's not a covering, we say it's ramified at some point. So this is sort of hard to say that it is ramified because 0 has no preimage for logarithm, but for root, it's clearly ramified. It has singularity in 0. It has multiple value in 0. This multivalued function, it's ramified in 0. Okay. Now I'm going to give you the important theorem which gives an example of multivalued function for associated with all this kind of theorems, Noether-like lemmas. So this is specially adapted to this particular proposition. And this is probably the only non-trivial theorem I'm going to tell today. So maybe I can have a break now and return 5 minutos per interval. Okay, let's prove this theorem. So the theorem tells us about a multivalued function given by monic polynomials. So you have z inside C n plus 1 given by one equation. So this we have the here coordinates z1 dot 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 z n and t coordinates, and z is a set of all z1 dot dot z and t, such that p of t equals 0, where p of t is monic polynomial on t with coefficients in these polynomial functions in first variables. So it's a polynomial ring with coefficients in polynomial ring. Do we say anything about its degree? Well, here it's not, but in fact, you can prove that it has degree d, where d is degree of the polynomial. Then z is a multivalued function from Cn to C. Yeah, and moreover, the projection from P from Z to Cn is a diffeomorphism in any point Zt such that P prime of t in Z is non-zero. So I take the derivative of the polynomial in t and apply it to the point Z. So Z is the first n coordinates and t the last one. And it just follows from the inverse function theorem immediately. It's something we have already done. So you have proof. Step 1. So first I'm interested in which points Z is a submanifold. And of course we have a map P from Cn plus 1 to C, and P minus 1 of 0 is our set Z. So Z is smooth in all points where dP is non-zero, right? This is inverse function theorem directly. Well, in particular, it's clearly, in that points, it's clearly smooth. Because here we have derivative even in one direction. So it's like derivative in all directions, and this derivative in one direction. If it's non-zero in one direction, it's non-zero. OK, so step 2. Z is smooth at all points what is my notation? ZT. The point is that this surjectivity here, it's surjectivity of a map to C. It's just that the corresponding function is non-zero because this is complex differentiable. So your a complex linear function is either to C is either surjective or zero. So it's smooth in all points CT such that dp at point zt is non-zero for all variables, like vectors, xi tau. Where xi belongs to generated by derivatives d by dz 1 dot dot d by dz n, and tau belongs to the space generated by d by dt. So it's vector spaces, tangent spaces. Okay, so now we take the polynomial p of zt and take its derivative, d of p of zt, like take its full derivative. It has one part which is, well, it's sum. So we take the monic part, dt times n t power d t power d minus 1. What is my notation for? It's also n. I'm sorry. It's an error. It shouldn't be n. It should be d because it's different numbers. So I assume that our polynomial p of t is equal to t power d plus sum ai t power from I equal 1 to 0 to d minus 1 t power I, where ai, it's also a polynomial. It's a polynomial on the first variables. So it belongs to C from z1 dot zn. Okay. So I write this as d t power d minus 1 dt plus sum d ai. This is differential of coefficients, which is proportional to d of the variable zi, t power I plus, and now we have sum ai times dt t power I minus 1. Okay, now we can see how this thing grows as t goes to infinity, and we see that this dominates the rest. So for very big t, this will stay small. This will stay, I mean, if t grows, this stays constant, and this grows much small, I mean, not as fast as. So the leading term, the term which grows the fastest for big t, term in t is dt. It's this d is different from that d. Well, this first d is degree and second d is, let's change the notation. It should be k. Sorry. So here it should be k, here it should be d, and it's from I equals 0 to k minus 1. Yeah. So the degree is k. And the leading term now is k t power k minus 1 dt plus the first term here. It's dA k minus 1 t power k. This is a term that dominates this sum for very big t. And it is non-zero. Is non-zero. Well, you see, this has two components, which are anyway linearly independent. So this component can be big, but it doesn't matter because this component is already non-zero. So this can be zero, can be non-zero, it doesn't matter. So this is non-zero. So it's smooth outside of a zero of something which is closed and nowhere dense. Okay, so now let's do more, like step 3. So take a smooth point. I'm interested where this map is locally, the projection is locally diffeomorphism. What, if you remember, what does it mean that it's multivariate function? That z is projected to C n with like generally a covering map for general point. So it should be locally diffeomorphism. So where it is a local diffeomorphism, we have projection yeah, so W here, it's supposed to be Z, well, maybe an open subset which is smooth. So pi from Z to Cn minus to Cn is locally diffeom. When its derivative is non-zero, this means that you have a vector. Yeah, so this is a smooth point. So its tangent space is n minus 1 dimensional. And when this when dp has the kernel of dp is equal to 0, but kernel is vertical vectors. It's vectors which go to 0 under this map. So kernel of dp is the set of it's generated. It's projection from n plus 1 dimensional space to n dimensional space, and it has one dimensional kernel. So kernel of dp is possibly, if it exists, is generated by 0 tau, where tau is this vector. Well, it was written somewhere. Well, tau is vector tangent to the last variable. Okay, so dp is isomorphism when dp big at a point zt applied to 0 tau is non-zero. Okay, Now I would express this thing in terms of derivative of P. So I write P prime, step 4. I write P prime of ZT is the same as dP dP of ZT by dt. Right? I mean, this is a definition. What I'm saying is that it is the same as this. Yeah, so, and it is clear. So this is the same as dP apply at the point ZT applied to 0 d by dt. So this is dP at the point ZT. So this means that Z is projected to Cn locally diffeomorphically at all points ZT such that P prime of ZT, P prime taken in T, is non-zero. Okay. I hope it's clear. I can repeat if it was not. Please let me know if.
Repeat the main plot.
Yeah, so we have this projection map from Z to Cn. What is its kernel? It's tangent vectors to this, which are proportional to 0 tau. If there are no such tangent vectors, we're done. Then it is an isomorphism. Because it's n-dimensional, this is n-dimensional. Okay, so this means that we need to take dP and evaluate it in 0, in the vector 0 and d by dt. Like a vector which is tangent to the vertical, to the last variable. But this is precisely the derivative of P in tau, in T. Yeah, by definition. So this is really a non-ramified projection. I mean, it's locally diffeomorphism precisely at the points where P prime is non-zero. This is more or less what we started from. That if you have a equation with non-zero differential, then it gives you a smooth variable, smooth manifold. So, but it's not only smooth, but it's projected to Cn non-degenerately. I can repeat. Clear? Okay, good. Now, there is this notion of symmetric polynomials. I'm now going to explain, to give precise set where this is non-ramified. It's called, well, the set where it is ramified is called discriminant of the polynomial P. And discriminant is defined in terms of symmetric polynomials. So I need to spend a couple of minutes on symmetric polynomials. This is elementary algebra. But since I'm using it, I'm going to at least give the definitions. I'm not giving you the main theorem. So definition, a polynomial P of Z1 dot 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 Zn is symmetric if the permutation sigma n permuting this permutation group acts leaves it invariant. So if P is sigma n invariant, where sigma acts on Zi by permutations. And of course, you have the canonical examples of symmetric polynomials. So you have polynomial P of Z1 dot Zn T, which is a product of T minus plus Zi from I equal 1 to n. And which is a sum of T power I, EI. When EI, they are clearly invariant under permutations called elementary polynomials, symmetric polynomials. And the theorem, which is, well, it is sort of easy to show, to prove using Galois theory over Q. And I don't know if there is Galois theoretic easy proof over Z, though you can probably use the notion of normalization and do a high-tech proof over Z. But it's, in fact, it's really elementary, and many people do its proof in high school because it's not hard. It's a high school level theorem.
Are they linearly independent?
They're even algebraically independent. So theorem.
But if you can prove that
Every, yeah.
then you can prove the rest by dimension counting, right?
No. It's polynomially expressed. It's not linearly expressed. It's polynomial expression. So every symmetric polynomial can be expressed, polynomially expressed through E1 dot En. It's n variables, so you have n polynomials. En is just product of them all, and E1 is sum. In fact, this is independent, so you have the polynomial ring from Z1 dot Zn, invariant part, equal to C of E1 dot En. In other words, Cn quotient by sigma is Cn. So this is high-tech versions of this, high-tech versions. This one and this one is high-tech renditions of this elementary high school theorem.
I think it is always true for any group-generated, finite group-generated by reflections.
Yeah, even by complex reflections, but this is out of scope. It's actually a hard theorem that. And the converse is also true. If the quotient is smooth, then it's generated by reflections. But these theorems are hard, and this is elementary. Okay, and if you never saw it, just sit and try to do it because it's not hard. It's just induction. You take a polynomial, you remove bits by bits, and you try to degrees to obtain something of lower degree, and then you repeat. And essentially by induction, by degree, which will give you this theorem. Okay, now I'm going to define you a discriminant of a polynomial. So definition. Consider a polynomial, so you have Z1 to Zn variables. You take a product for all I not equal to j. z1 minus zi minus zj is symmetric in zi, right? You exchange them. Well, they'll go in pairs here. So if you exchange them too, the sign will change twice. This means that the sign won't change at all. So if you do like, this is the same as you take I smaller than j and take square here. Maybe it's more clear. Well, it's the same as product for I not equal to j, zi minus zj. Okay, so d of E1 dot En. Do I have any notation here for this guy? Well, so it's a P of Zi. It's called discriminant of E1 dot En. So I express the symmetric polynomial in terms of the elementary symmetric polynomials. So this is and this gives in fact, this gives you a nice result, remark. D of E1 dot En is equal to 0 if and only if the polynomial P of t, which is equal to product, well, sum of ei t power I, has multiple roots. Has multiple roots. This means that it has some of the roots have multiplicities, bigger than 1. Because if it has multiple roots, the roots can be expressed through zi. So if some of zi's are equal, this means that your polynomial p has zeros. And p is precisely this expression through d is expressed through the coefficients. It is equal to the product of difference of all roots. Again, you can express it explicitly for quadratic and for the cubic here expressions. You can find them in Wikipedia. So b squared minus 4c is something that even high school students know, because it's the discriminant of quadratic polynomial which you use to express it roots. And then discriminant of cubic polynomials probably could be also used for to find explicit solutions. I don't know, but here it is. Okay, so discriminant is non-zero if and only if this polynomial has no multiple roots. And we're interested in that for the following reason, because we are interested when derivative has zeros in a point in the solutions of the polynomial. But the derivative has zero in solution of in the root of the polynomial precisely when there are multiple roots. So we have a nice corollary of this whole business. Well, it's corollary of this claim which became a remark here. So we already had a corollary 1. I'm sorry about this, but now this becomes corollary 1. So corollary 1. Consider a polynomial p of t. We don't need algebraically closed field, I'm sorry. Any polynomial, but a polynomial over k over a field k. D is discriminant. And p of t is non-zero in all roots of t, if and only if. Well, maybe you need algebraically closed because you might have like, so what is true, it's non-zero if p and p prime are coprime. But then they possibly have a common divisor which has no roots. And then, yeah, so it's k algebraically closed. So it has no roots at t. Yeah, p prime of t has no roots, is non-zero in all roots, if and only if d of p is non-zero. And proof, if A is a root, K is a root of P, so P of T is equal to P A of T, some polynomial smaller degree, times T minus A. All right? And then P prime of T is P prime of A of T plus P A of T times P A of T. Here you have T minus A, sorry. Okay, so P prime of A is equal to P A of T. This implies that this is non-zero precisely if P A of T is non-zero, and this is equivalent to A being not a multiple root. So in other words, P of A is equal to 0 if and only if P is divisible by T minus A squared. Clear?
There should be here A, but on the last line. If P prime of A of you just put like A
Of A here? Okay, thanks. Yes, of course. Thank you. Good. So this is elementary, but it's in fact related to what we need to do now. And we are interested in this multiple function defined by the subvariety, which is associated with the polynomial. Okay, so theorem. So you have P of T inside C of Z1 dot Zn and T. So it's a polynomionic on T. And Z, it's corresponding, it's zeros, corresponding subvariety of Cn. So this is the guy which is finally projected to Cn. And I am interested in having the set where it is non-ramified. This projection is non-ramified when there is truly a covering. So we take d of z. D of z it's a polynomial in C of z1 dot Zn is discriminant. Of P. So it is this polynomial which is associated with the coefficients. And take U. U inside Cn is the set of all points. It's Z inside Cn such that D of Z is non-zero. So this is the points where it has no common roots. Then Z intersected with P minus 1 of U. P is our projection. So P is projection to Cn. This is forgetful map which forgets T. Is smooth. And the projection from this to Cn without, well, to U is, so let's suppose this polynomial, well, is K treated smooth covering, where K is dimension of the polynomial, degree of the polynomial. K is degree of P. Well, there are 3 points, but steps, but in fact the proof is entirely elementary. Is this statement clear? So you have this projection. Sometimes it has multiple roots, but outside of multiple roots, this is just distributed cover. So proof. So you have P of Z of T has K different roots at or any Z inside U, right? So you plug Z here, you obtain a polynomial on T, just complex valued polynomial. And this polynomial has no multiple roots. So it has precisely D roots. And in fact, since P prime of Z is non-zero, the projection from Z to Cn is non-ramified, has surjective differential. This is something we had previously, that it has surjective differential precisely in the points where the derivative of P is non-zero. And then it is locally diffeomorphism by inverse function theory. In fact, if your polynomial is well, you can look at Galois group action of the corresponding finite extension, and then it would actually exchange you the sheets of this Z of this projection. So it will be actually a group quotient, which is not obvious, but if you work with Galois theory a little bit, you will see. But anyway, it's really not hard to see that it is a covering, because it is its derivative is non-zero in all points. So it's yeah, and it has precisely key preimages. So it is key sheeted covering. Okay, it has. Now we can use Noether normalization lemma. And apply it to obtain that this can be actually applied to any algebraic variety. So every algebraic variety can be obtained as a multivariate function on Cn, like a yeah, well, more or less. So corollary. Suppose you have X algebraic variety, well, affine variety. Then there exists aberration finite map X to Z, a divisor D inside Z, and Dn and D1 inside Cn, such that Z without D admits a k-sheeted cover to Cn without D1. So Z is a total space of this multi-valued function, and X is obtained from this Z without D by gluing in some divisors. So proof. Proof is directly follows from one of the form of Noether normalization lemma. So you have X goes to Z is birational, and Z goes to Cn. So Z sits inside Cn plus 1, and Z is the set of all X such that P of Z of all pairs Zt such that P of Zt is equal 0, where P is monic polynomial. This is Noether normalization lemma precisely. So we took we take X, we replace X by normalization, then it's normalization on something which is a divisor. So X is a birational to Z, and Z is projected there. So after you remove, and then the birational maps is isomorphism outside of a divisor. This is something we had already. So this means that X without a divisor is k-shaded cover of, and then yeah. Okay. So we apply non-normalization lemma. We get that X is bidirectional to Z, where Z is given by a single polynomial equation. This is something we had. If you remember, we just took a projection to, it was obtained by using the primitive root theorem. We proved that there exists a we take, let's, yeah, these coordinates were our transcendence basis. And then there was another coordinates which already generates the field of rational functions on X. And then the image of X in the closure of the image of X in this product was given by a single equation. This is because it's just, I mean, the corresponding field is given by this equation, and then X is bidirectional to this subset given by this single equation. So X is, and there is a corollary. Very nice. And this is actually the main utility of this. Well, maybe not the main utility, but it's definitely for us, this is like a crowning achievement, because it's funny, but it's not obvious that every algebraic variety has a single smooth point. I mean, we have this huge algebraic geometry, and we have this nice complex analysis and complex arguments, but complex arguments are applied only to smooth manifolds. And if we have no smooth points, we cannot even hope to apply them. Now we can. So corollary, every algebraic affine variety X inside Cn has a smooth point. This means that you point X small inside X big, such that X big is a smooth, and a neighborhood, U containing this X, such that intersection of X with this U is smooth submanifold. In other words, this means that every algebraic variety is smooth generally, and it has some singularities which we have no control over, but it sort of makes a nice picture. You can like find any graph and try to like write solutions of polynomial equations like x squared plus y third plus xy plus 1, something like that, on a paper, and you will see that it is indeed smooth with maybe some single self-intersection points or something. It could be things like that, could be double intersection point, but generally it's definitely smooth. And this corollary proves that it is true, generally. So whatever equation you write, as long as it's non-empty, it will have smooth points. So proof. Well, we have X without D is ramified cover over Cn without D1. Ramified, well, it's non-ramified, so it's a smooth, so locally diffeomorphism. And then these are smooth points. They are smooth subvarieties. Of course, you can, if you are interested not in coordinates and you want that to be like to have it. And we had, if you remember, we had two definitions of manifolds, one in terms of charts and atlases, another in terms of ambient subvarieties. So you can actually do that, try to do this with the coordinates and you will see it. So this argument will also give you some neighborhood which is diffeomorphic to Cn, but I think this is already good enough. Okay, so I'm not sure how many sessions we will have, probably just one. So next time I will not will we have a session próxima aula será? No, quinta. Sexta também? Oh, tá bom. We'll have two sessions where I will explain how to do in commutative algebra the same procedure, how to define smooth points. They will be called regular points, and how to work with them. In particular, we'll see that smoothness in dimension 1 is precisely the Dedekind condition we considered on the previous lecture. Obrigado.